Okay, so how was everyone? I already said that. You missed it. It was a fantastic joke about this. You don't get the solution. Yeah, I know. Multitasking is supposed to be the specialty of your generation. I'm glad that you're here. Very well. Okay. So we talked last couple classes about this class of languages, C and C++ being among them, where as a programmer you're responsible for managing the lifetime of dynamically allocated objects. The lifetime begins when you say malloc or new, and it ends explicitly when your program does something, either calls in the case of C3, or in the case of C++, for example. And in these languages where you explicitly delete things, there's the possibility of this bug called a dangling pointer. And a dangling pointer occurs when you have a pointer that points to an object, and usually the way this happens is another pointer too, but you can see this in this case like this, and you say free, this becomes nothing changes about memory, but this becomes available for reallocation. And sometime later in the program, you'll create another, you'll say malloc again, and have another pointer point to this. And now you have this old pointer, that's the dangling pointer, that's pointing to an object that is in use by another part of the program. And sometimes I've drawn it here as if, this is, they're both pointing to the beginning of the object, but it doesn't have to be that way. In fact, it could be like this. And that could point to the middle of the object. And we saw the problem with this is that this is x. You would say something like star x equals 0. This writes a 0 right into the middle of that object. And so we have this problem where a bug in one part of the code, this is the black code, creates a problem for a completely unrelated part of the code. The only reason that, the only thing they have in common is that they're both sharing the same key. Right, and there's just one key. Questions about that? Is everyone thinking about this? You see this in 221 too, right? Like you probably talked about it. Someone told me that you learned about algorithms. We'll talk about algorithms. That's a way to detect memory. One thing you can do to completely eliminate dangling pointers is never call free. Or there's a corollary or a complement to this bug of dangling pointers is basically call free too soon, calling free too soon. If you don't call it often enough, or you don't call it at all, that creates the other problem, the memory leak. So memory leaks are sort of on one side of the problem and dangling pointers on the other. And of course the goal is to have neither of these bugs. And the only way that can happen is if you make that happen as a programmer. So we're going to talk today about some best practices. And for sort of the easy case first, and then we'll look at the hard case in the second half of the class. Okay, so this is a common idiom for dynamic allocations here. Sort of like producer and consumer. You have one part of the code, in this case, receive is in that part. That says, I'm just going to abbreviate things a little bit. Something like that. Right, so it allocates something in return. if you think about Java programs you've written, you've done this a lot, actually. Many procedures that say new in them. Do something and return. The point is the thing they just allocated. So in many ways, the purpose of receive is to create this mBlob. And then it fills it in. So remember, this is taken from the operating system. It's receiving a message from the network. So it fills it in with the bytes that came in over the network, and then it returns it. So that its goal is to produce message packets. And then you have the consumer, some other part of the program, which here I just called void. That calls this and saves it in the local variable. And then in the simple case, the complicated case is that you don't know whether you're supposed to call free here. We'll talk about that later. But if you know you're supposed to call free, then you write free. Okay, so I have in one part of the program, in one module of the program, what's another word for module in Java terminology? Class. Somebody say class? Yes. So when I say module, I kind of mean class. What I mean is a contained piece of the system that has a public interface and a private implementation, just like the class. So when we're talking about classes in 210, that's really modules. We're talking about modularity, which is the core engineering technique for all software. Is the way we implement abstraction is modularity. So this is in one module, the public interface you see. This is in another module, I don't know what it is. And they connect in two ways. So one way they connect is who calls the procedure, the public interface. And the other way they connect is they're sharing responsibility for this dynamic allocation. Malloc is called here. Free must be called here. Now I want you to discuss this with each other, and knowing what you know from 210, analyze this design. Does it have any weaknesses? So what do you think? Who likes this? Perfectly fine, no weaknesses. Who sees a weakness? So I got like 6 people who see the weakness. Nobody thinks it's fine. So what's the other category? You think there probably is a weakness, but you can't see it. And it's only because I wouldn't be talking about it, right, if there wasn't a weakness. So that's kind of like saying, I don't think there's a weakness, let's say that. So most people don't see it. A lot of people do. So some of you did. Yes?
It requires the person who's writing the code to remember to write free.
Bingo. So the problem here, so we think about one of the concerns in this program. You think a concern is just, something you have to do, something you have to implement. Cuts across 2 different modules. And that concern is the management of this object. And so when we think about that concern is not cohesive. It's a little bit in this module and a little bit in this module. Or we can think of it another way, to use the other term from 210, is that this creates semantic coupling between these 2 things. It's like if I don't call free, then I create a memory. If I call free at the wrong time, I create a dangling pointer. And there's nothing here explicitly that signals that I should do this. Okay. Now, one solution to this would be to have some kind of coding convention that would tell you, like in the comments or in the specification, to receive, tell you you must call free. But that's error prone. And many companies will have this. When co-ops are doing C programming, they're going to have some rules about when you have procedures that either take as parameters or return as values, pointers, what you're allowed to do with it. It's not embedded in the language, and even when you have that, you still have this cross-cutting nature of the management of that object. Does that make sense? You see that? It's like you malloc in one thing and then a completely different module. So this module, if I look at this code, just this code, I can't tell whether this program has got a memory management error. I can't tell if, while I return this, and it'll all depend on what foo does, whether this is going to end up being a problem. And when I'm looking just at this module, the potential error is I don't remember, I don't notice that receive it, I'm supposed to free that. So what do you think might be a way to solve this problem? So the problem is that malloc and free are in two separate modules. Put both of them in one. Yeah, so this is the first basic rule. Well, I would say that the 0th basic rule of dynamic allocation is don't. If you can possibly avoid saying malloc, you will never have a memory leak or dangling point. First, but dynamic allocation, of course, has many, many benefits, so most of the time we'll be able to do that. So the first rule is, whenever possible, co-locate malloc and free in the same module, and even in the same procedure if that's possible, but that's not necessary, just in the same module. And that gives you a way to look at a module as a separate thing, and debug and test and debug that to ensure that that module, all by itself, without worrying about any other part of the program, is free of these two bugs. So how would you do that here? I'm either going to have to move free here or malloc here. Would moving free here work? Well, no, because I really do have to have this dynamically allocated thing that has the message, network message inside it, that foo can consume. So it must be the case that I'll move malloc here. Right, so if we look at the new foo, it's going to have this. So struct star MD and B is malloc. And then we call receive. Leave it open for a moment, and then call free. So this is good. Right now, that concern is entirely cohesive within this module. No other module ever sees this the malloc with free. Now, the pointer does move back and forth with another module, perhaps. As long as that module knows it's not allowed to free it, then everything's fine. So, how would you change receive to make this all work? Oh, discuss that. I think the answer's on the slides. So what would I do? Suggestions. pass it as a parameter. So I'll make this a void. So I might say, MB, arrow, size equals some number, and then copy, whatever the fields are that I'm copying the data into it. Would actually be, maybe MB data equals something. These are the things that happen here. I don't malloc here, and I don't return anything. I just simply pass into that procedure a pointer to the object. So we compare these two things. What happens here is that I have a local variable MB. I call malloc. I get a buffer. I then return it. So when I return it now, at this point, this variable MB, right after, now points to that. Right, so this is step 1, and that's step 2. Now at this point, right here, that variable's gone away. When this procedure is returned, there's only one reference left, and it's this one here, and then I'll save it. Right, so what happens here is you allocate the object here, you return the pointer here, and then you use it here, and then you free it. Whereas over here what happens, I think my mic is over here what happens is that I have a variable MB, and I allocate the object here, and then I pass it as a parameter. So here it is. And this procedure uses that to do whatever it wants, copy things in, and then it just is done. And then the foo procedure continues now with this pointer to the same object, but with the object having been modified by the call to receive. Question like that? Yeah?
So in the new receive, you reference MB and call size. You're not changing the size of the memory. That's like a member.
Yeah, so this, maybe I shouldn't call it size. I'm just saying these are fields of the struct. I was just trying to give you an example of what, how the MBUF contents change. So this is the size of the field here in the data. Thank you. Other questions? You can make this even a little bit better by rather than allocating the buffer here, we could make this a static struct as a local variable. As soon as I get there. Batteries, I'll show you. So what we can do instead is do this. No stars. And then just return. So we'll see later that this is allocated in a different dynamic region of memory called the stack. Don't worry about that for now. Just think about the fact that what this variable is the entire struct. It's not a pointer to the struct. So here I create a box. Here I create the whole struct. Right. And then I pass into receive a pointer to the struct. and then it does the same thing. Okay, so from the perspective of receive, it doesn't care which way I did it. And what's nice about this is I don't have to call free. Free will happen automatically when this procedure returns. Now you might say, well, that's the same thing here. That MB, that variable automatically disappears. This variable was dynamically allocated on this stat thing, and that variable automatically goes away. So why do I have to call free here and not here? This is a question for discussion. So why do I call it here and not here? So discuss that with each other. So who has an answer?
In the second one, the data that's being pointed to is inside the function itself, so it gets free alongside with other variables. Whereas in the first one, the data is external to the function.
Right. So this is a good description. Might say it another way is that in this example, there are actually two different things that have been dynamically allocated. One is the variable MB, but that's just a pointer to the object. And that's created when the procedure is called. And we'll see how that works later in the course. The other one is the object itself, the struct itself. And that's created by malloc. And so if this variable goes away, but you don't say free on this, that's memory leak. Just this one going away doesn't make that going away. This is just the pointer going away. Whereas over here, this is the entire mbuff. There's just one thing. And so when it goes away, the mbuff goes away. So either of these, this has the advantage you don't have to remember to call free. In a small procedure, it's no big deal. In a big procedure that has like if statements, and especially which C doesn't if you had exceptions, there might be multiple control flow paths out of this procedure, and you have to be sure that you call free on all of them. Now, if you're doing this in Java, you can do that with the finally clause and the try catch, and put free there. Here, you don't have to worry about that. Every control flow path out is gonna cause that to happen. And what by control flow path, you know what I mean? It's like if I have an if statement here and I have a return, so you don't actually get to here. Before that return is up here in the middle, you have to call free there too. Okay? But we'll see later that this that has an advantage over this when it comes to what happens if you were to accidentally overflow this function. So either of those are fine. Both of them are much better than this. Right? Okay. So let's look now at another example. This is at the end of this. What I'm illustrating is this. I've mentioned it once before when we talked about array overflow. And here I'm coming at it again, and we're coming at it a third time when we actually show you how to write a virus to attack a program with this vulnerability. But this is we'll illustrate a classic vector for, by classic I mean like widely exploited vector for infecting programs with viruses if you get this wrong. So, and it starts with a string. So strings in Java are what? How would you say what a string? No, it's not an array of characters in Java. It's an object. It's an instance of a class. This name string is a class. And it has fields in it. And the two fields it have are length and the data. Now the data is an array of characters, you're absolutely right, but there's also a length. So Java strings know how big they are, which is kind of obvious. You need to know how big a string is, right? Right, so how big is this string? 2 characters long, but it actually is 2 bytes long if this is being encoded in a certain way. There's multiple different ways to encode characters. The characters that are in our alphabet can all be encoded with a single byte, so that's often done that way, but it could be 2 bytes for each character. But anyway, it's 2 things. In C, a string is just an array of characters. It's just this string. And this will have a size, right? The size will be, I'm going to say S, malloc, something. So the size of this is 100. That is the size of the array, but that is not the length of the string. C determines the length of a string by looking through the string from the beginning and counting how many characters there are before you get to a null. In C, strings are always arrays of characters, they're not arrays of integers. In C, if I put something in single quotes, that's a character that it's just another array of whatever the number is that corresponds to capital H. And this is 0. And there is a function that you can call, it's strlen, that will do this, and it'll count how many characters are in the string. And if I call that, what should the answer be? 2, right? There's 2 characters. 1, 2, and then the null. And if I do this, size of S, what am I going to get? It's not 2. I heard somebody say 8. Did we say 8? Who said 8? Anybody say 100?
100.
Got 100? 100? So maybe it's 100? Anybody got a different number? 8, thank you. Maybe it's 8? Anybody else? You said 2? You're good, you're good. You see what's not 2. Okay, so remember now that size of computes statically the size of whatever its parameter is. Is 100 a statically known thing? No, right? Because this is, I mean, here it is in this example, I wrote 100 there, but there may be many places in the program that assign values to S. Maybe there's another place that says S equals, say S, 50. So that number, the actual size of this array, is a dynamic property of the program. Size of couldn't possibly tell you what it is. All that it tells you here is the size of this pointer, which is 8 bytes. So how do you get to 100? You can't. You just have to know that as a programmer. Now, if you wanted to save it someplace, you could do it. Do something like this now. In this case, this is the length, that's the 2. But you could, if you wanted to, you could have another variable somewhere that kept the size of that. But you can't tell the size of the array that contains a string. You can tell the size of the string. This is what's going to become important. Does this make sense? Okay. So we're going to look now at a very simple and very common thing to do, which is to copy one string into another string. So this is essentially like, saying x equals pi. So sort of like that. I want to copy that string into whatever, this isn't the right syntax, but into x. So x now points to that string. Or In other words, I have an X, which is an array, a Y, which is an array. I'm going to copy all this stuff from here to here. And you can see the implementation of it. Here's what you do is you are given a parameter, which is the source string. You call a procedure that gets its length. Then you malloc something that's that length plus 1. Why is the plus 1? The length is 2, but I need to have room for those two plus the null. Okay? So my destination string is just going to be exactly big enough to hold that string. The source array might be bigger. The destination array will just be exactly the right size. And then I go through a loop where I copy, starting at index 1, from the source to the destination. Destination sub I equals S sub I, and then copy the next one, 2 and 3 and 4, all the way up to the length plus 1. So I'm copying, in this case, when I have 0, 1, 2, when I get to 3, I stop. So I've copied this, this, and this into the destination array. And then I return that to a program. And so here's, in another part of your program, in a separate module, like that copy is going to be in the library. So your program is always going to be a separate module from the library. What you do is you call copy, you put that in this destination pointer, then you print it, do whatever you want with it, and then call free. Now this program is correct, it's error-free. If I hadn't called free, this program would have a memory leak. But there might be something wrong with it. There might be some way to write this in a better way. So I want you to discuss this with each other now. Is there anything that you don't like? Is that a question or an answer?
An answer.
I don't want to answer yet. So raise your hand if you see there being something wrong with this, if you know that there's a better way to do